Okay, we were discussing the memory interfacing in the last few lectures. There is something important that I forgot to discuss in the previous classes. See, I have taken a 2-bit register here. So with 2 flip-flops which can store 2 bits. Okay, and we have seen that the input data is written into the memory by using the write signal, and you can read the information from the memory by activating read signal. Okay, and of course this enable pin must be set to logic 1 before you write some data into the memory. Okay, so when now you have, this is for one register, so when you have a series of registers what we call as memory, suppose I take a register or memory which has 4 registers, and each register can store 2-bit information. Okay, so you can say, okay, 4 into 2 bit register. Okay, so 8 bits, but they are stored in 4 registers, 2 bits in 1 register. So 2 bits will be stored in this location, 2 bit here, 2 bit here, and 2 bits here, and so on. Okay, it means you have one more structure like this, just like this register. You have one more 2-bit register. Two inputs and I1, I2, 2 outputs which are controlled by your tri-state buffers. So this is output 1, this is output 2. So you have again here, this is tri-state buffer which is connected to your right pin, and the output buffers, they are enabled by using the read signal. Enable, of course, you have enable pins, they are connected together. Okay. So this is another register. So this is one register 2-bit, another register 2-bit, then we have one more 2-bit register, one more 2-bit. So 4 registers are there. Okay, now when you read or write data from this memory, it means at a time you have to select one register only. Okay, and that we have seen that it is done by a decoder. So if you have 4 memory locations, so you can use a 2:4 decoder. Which will have 2 address lines, A0, A1, and of course it has 4 outputs. Okay, and each output of this decoder is connected to one of the enable pins of these registers. So it may be connected to this may be connected to this, and similarly rest of the 2 outputs, they are connected to rest of the 2 registers that I have not drawn. Okay, now when you want to read some or write some information into the memory, so you have to select one register, one of these 4 registers. So how that is done? That is done by the addressing. Okay, so if you have address is 00, so only this pin, suppose pin number 0, 1, 2, and 3. So when the input address is 00, your pin number 0 will go high, rest will be at logic 0. So you enable that register which is connected to this enable pin. Similarly, if your address is 11, so this output will be high at pin number 3. All other outputs are 0. It means this register will get selected. Okay, so once you identify the register and you send a control signal right, so whatever is data on the input lines, that will be stored in these 2 flip-flops. Okay, all the input lines of all the registers or all the flip-flops, they are connected together, that we have discussed using a data bus. But at the same time, the information can come from one of these inputs only. Okay, because other inputs, since their enable pin is 0, so you cannot write some information in the flip-flop, even if you apply some read signal here. Okay, so the write signal here, so that will of course activate these buffers, but since the enable pin is at logic 0 for other registers, so there will be no changes in the memory cells. Okay, so for write, okay, this is okay. Now for read, what we have said, that when you press the read signal, okay, so all the buffers in all the flip-flops, they get activated at the same time because they are all connected together. So this read and this read pin, they are basically connected together. Okay, all the 4 pins, because at the output of this memory chip we have only one read signal. The single read signal is used to activate all the buffers, whether it is in this register or is in this register or this register. Now what is the function of address decoder? To decode the address or to identify the memory location. But as far as your read operation is concerned, whether your enable pin is high or low, because the data is already available at the output of flip-flops, it is already stored there in each register. Okay, so once you send a control signal, what will happen? All the buffers will get activated. Okay, it means data from the first register will also come on the output or data bus. The data from this register will also come on the data bus, and so on. Okay, so what you need to do is that it means you have to design some way in which once you send a control signal read, so the data must come to the output from one register only. Okay, it means these buffers, they must not be directly connected to the read signal. Okay, because if you connect them directly to the read signal, all the buffers will get activated. Okay, so you have to use a combination of enable pin along with the read signal, so that when enable is high and read is low, only then a particular buffer will be activated for a particular memory location or a register. Okay, so how you can do that? It means what should be my combination? So I have 2 inputs, one is now enable, one is read, and what I want at the output of the buffer. So when this enable is 1, okay, it means we have identified this memory location by using enable as 1. So it comes from that this address decoder. Okay, and your read signal is 0. In that case only your output must be 0. Okay, so for other cases, if it is 0 0, it should be 1. If it is 1 1 1, it should be 1. And of course if it is 0 1, it should be again 1. Now this is what, this is output to the buffer, not output, in fact buffer control, you can say input to the buffer. So input signal to the buffer should not be directly connected from the read pin, because that will control all the buffers irrespective of this enable pin. Okay, so you must have a combination of enable pin and read, so that when that enable is high, it means you have chosen a particular or identified a particular memory location, and then you send a control signal read. So data should come from that register only. Okay, so you can see now you can create what should be the, this is a combination logic circuit now, so you can find what is the output, right? So if you simply use k map, so you have 2 inputs, one is maybe enable, one is read. So 0 1 0 1. So for 1 0 it is 0. Okay, 1 0, it is 0, and enable is 1 and read is 0. So enable is 1 and read is 0, it is 0. For all other cases it is 1. Okay, so you'll get 2 groups. So what will be my output from this? This should be, if I write it as suppose any signal x and read bar denoted with y, so it is enable, which is now x bar, in fact, or I write it as x bar plus, this is x bar, this is your y, so x bar plus y. Okay, this is my combination circuit now. It means this enable pin, you have 2 pins now, one is enable and one is your read. So you have to use the inverter here to make its complement, and then you have to find a OR operation, OR gate. Okay, now this is the output which is basically used to control this buffer, right? So this enable pin, so if you see here, let us suppose for this case, so you have enable signal which is of course connected to all these pins. So this, to generate this buffer control logic, you must have a connect this to the inverter, and this read signal, it must be combined with this using a OR gate. Now this is going here, okay, this path, this is not directly going here, and the output of this OR gate, now that is used to control this buffer. Okay, so if you have a situation like this, now you can read the information from a single register only. The data will not come from every register on the data lines. And how it is done now? Let us suppose you have some address here, any address. Address can be, it can be 00011011. Okay, so if you place some address on this address lines which is 01, suppose, it means your second register is identified. So once you identify this second register, it means the output of this decoder, in the decoder this pin will go only high, rest of the pins will be at logic 0. Okay, so this pin is high, it means enable is 1. So when it comes to this, it becomes 0. So read signal is already 0, so you get a 0 here, so this buffer gets activated. Okay, now what about the other registers or other buffers? See, at pin number 3, which is connected to this, you have 0 here now. Okay, if your address is 01, if you have 0 here, and when you have used here again a inverter circuit, this mechanism has to be done for all this. Okay, so you have a inverter circuit here, and then it has to be combined with this read signal again using a OR operation. This has to be connected with this. Okay, so if it is 0 here and 0 comes from the read signal, so 0, this will give you 1, so 1 plus 0, it will give you 1. It means this buffer will not be activated. Okay, so at a time you can read the information from this register or this register or this register. So this is how now your address decoder is identifying the memory locations. This, okay. See, although this concept I have not obtained in any books, but when I was going through this, I realized that okay, once you press this read signal, all the buffers, they get activated at the same time, so the data will start flowing from each memory location on the database. Okay, so to control this, this is the possible solution. So you may see for some other solutions for this also. Okay, and one thing more that we have discussed in the last class that suppose we have seen that if you want to attach a 1 kilobyte memory with a processor, so what happens is that your processor has 16-bit address lines, A0 to A16. Okay, of course there is demultiplexing in between that, you know now. And if you interface a 1 kilobyte memory, that is you have 1024 registers, so you need only 10 address lines, that is A9 to A0. So A0 to A9, they will be connected with the internal decoder of this. The internal decoder inside the memory. So they will be used to identify these 1024 registers. Okay. So the 6 address lines which are left now, that is A15 to A10. So we have used them for chip select. Okay. So the chip select or chip enable pin on this memory. So along with this we have a read pin, of course, you have a write pin. So these 6 address lines, they were used to decode this address. Okay, so you can use any combination, any hardware that we have already discussed. Okay, so one possible solution for this, that okay, you suppose you connect all these 6 lines, that is your A10 to A15. If you simply connect them with a NAND gate, and the output of this NAND gate is now used to select this chip. So this chip will be selected when all these inputs are at logic 1. Okay, it means you have to permanently tie these pins to plus VCC, apply VCC plus 5 volt. Okay, and of course these 10 bits, so they can go from 0000 to 1111, any address. So this is how you do the address, how you identify the address range and address map. Okay, now one more way to do this is that in place of using a NAND gate or some other hardware logic circuit, you can use a decoder circuit here also to identify the, or to select this chip. Okay, so what we do in that case, let us suppose I take a one very practical case. Suppose you have a memory, this is EEPROM, erasable programmable read-only memory, and it is 4 kilobyte memory, 4 kilobyte. Okay, 4 kilobyte means you need 4096 registers, each of 8 bit. Okay, so how many address lines are required? Yes, it's 4 kilobytes, so 4 KB means that it is 2 raised to power 12. Okay, that is 2 into 2 into 2 to the power 10. So 2 to the power 10 is your 1 KB. So 2 into 2, it becomes 4 KB. So you need 12 address lines now. Okay, it means your A0 to A11, now they are connected with this memory chip. Okay, so this is a chip available basically, which chip number is 2732. And then of course we have 8 output lines. So it is suppose 0 to 07. I'm talking about ROM, so it does not have any input lines. Okay, so you have only output lines here, which are connected to your data bus. Okay, so this is connected to your D0, this will be connected to your D7, and so on. Okay, now along with this, you have a chip enable pin here, chip enable or chip select, and you have one signal for read, because now it is a ROM, so you can only read the data, you cannot write the data into this. So this is read, and anyhow in some of the chips it is given as OE, output enable, active low pin. Okay, so this is same as the read pin. Now you have used 12 address lines for locating the memory location. So you are left with now how many address lines? 4 address lines are left. Now those 4 address lines, they can be combined using a logic circuit to activate this chip, that you know. Otherwise what I'm saying is that you can use a decoder for it. Okay, so if you use a 3:8 decoder, so you have 3 inputs, you have 8 outputs. Okay, so we are using a decoder here, which is 74 LS138. Okay, so this is 3:8 decoder, and it generally gives you active low output. Okay, so all the outputs, they are low. Okay, so you have output 0, this is output 0, output 1 up to output 7, you have 8 outputs here. Okay, and along with this chip has 3 enable pins. One is your active high, this is E1, active low. Another pin is your A2, active low. Another pin is A3, which is active high pin. Okay, now what I'm saying is that I want to use this decoder for chip enable. Because I have already used 12 address lines for decoding the address, I am left with 4 address lines, and those 4 address lines are now A12, A13, A14, and one more line is now we have A15. Okay, now this what this decoder will do. At a time, it will give only, or it will activate only one output. So that depends upon what is the address at the input lines or the 3 input lines. Okay, so if it is 0 0 0, your this output will be activated. Now since it generates active low output, it means this will be 0, rest of all this will be 1. Okay, so if you give input as 0 0 1, so the second output will be at logic 1, rest of all them will be at logic 0. So if you want to use this output of this decoder to enable this chip, it means one of these outputs, any one of these outputs, that can be connected with the chip enable, because it is generating active low output. Okay, it means suppose if I am using O0 as input to this chip enable, or chip enable is connected to the output pin, that is O0 of this decoder, it means what should be my address here on the 3 inputs? It should be 0 0 0. Okay, if it is 0 0 0, then only you will get output here 0, rest will be output 1. So this will automatically enable this chip. Now what we have to do with the fourth line, A15. So this A15 can be simply used to connect to one of the enable pins. Okay, so you can connect this directly to this, or there is a possibility that you connect to the inverter and so on. Okay, so rest of the 2 pins, enable pins, so since we are not left with any other address lines now, so you can simply make it ground. You can connect this to ground so that it is permanently enabled, and this you can connect to plus 5 volt so that it is permanently fixed at logic 1. Okay, so such a scheme you can also use to decode the address. But for this case, if I use this as my logic circuit, what will be the memory address again? So you have A0 up to A11, 12 bits. So they can vary from now 0 0 0 0, right, go up to 1 1 1 1 1 1 1 1 1 1 1 1, because we have 4 kilobyte memory, so 12 address lines are required. And then the remaining addresses A15, A14, A13 and A12. Now this we have fixed. Since we have used output 0 of the decoder to control this chip enable, it means the address that I must place on the input of the decoder, this should be 0 0 0. So these 3 pins are now fixed at 0 0 0. Okay, similarly, since I am connecting A15 to the enable chip of this decoder, and since it is at active low pin, so it must also be 0. So these 4 bits now they are fixed. Okay, and this can vary from this to this range. It means what will be my address for this now? So this is 0, this is hexadecimal, this is one other 0 0 0. So it will range from 0 0 0 H, it will go up to 0 F F F H. Okay, so here 409 locations, the starting address is this and the ending address is this. Okay, so again you can change this address. You can, this is what we have discussed in the memory mapping. Okay, the address can be changed by using a different logic circuit for this chip enable, right? So how you do that? If suppose I use the same decoder, 3:8 decoder, the same IC with 3 inputs and 8 outputs. Okay, we have 3 enable pins, one is active low, this is also active low, this is your active high. Okay, so this we have connected to 5 volt, this we have connected to ground. So you are left with 4 address lines, A12, A13, A14 and A15. Now in place of suppose utilizing the output 0 of this decoder, I am suppose connecting output 7 with the chip enable. Okay, because you have to just connect one pin, output pin, to the chip enable. So any one pin can be utilized. If you connect out 7 or 07 pin of this decoder, it means this pin must be at logic 0, rest has to be at logic 1. So in that case, what should be my address on the address lines? It should be 111. Okay, A12, A13 and A14, this all must be 111. Then only at 07 you will get a logic 0 signal, which will enable this memory chip. And A15, again, since it is a active low pin, it means you have to keep this A15 to logic 0. Okay, so you can keep it at logic 0. So it means it has to be permanently tied to the ground. So these 3 pins must be permanently tied with the VCC. So what will be my address in this case? Now these 4 pins that I have used here, of course this is fixed. Okay, so your 12-bit address, this is fixed. It can go from 0000 to FFF. So but this 4-bit address, now that depends upon this decoder connections. Okay, so like now in this case I am using 07 to enable this chip. It means A12, A13 and A14 all are to be kept at logic 1. A15, 14, 13 and 12. So these has to be fixed at logic 1. And if I am simply connecting A15 with this, it means it should be kept at logic 0 because it is a active low pin. So memory address will start from this. So this, what is this number now? This is 1, 2, 4, 8. So 4 plus 2 plus 1, it is 7. So to start from 700H to 7FFH, isn't it? So you have different address range here. For this circuit you have different address range here. Even if you take one more case, if I just in place of this A15, if I not directly connect this to this, in between if I use the inverter circuit here, a NAND gate, sorry, this NOT gate, it means to keep this at logic 0, now this input must be kept at logic 1. Okay, now in this case all the 4 inputs, they should be at 111. So it will be 1111. So it means it is now F. So in that case your memory address range will be from F000 up to FFH. Okay, if you have used the inverter circuit before E15. So the conclusion is that you have 60 in 8085 you have 16-bit address bus, A0 to A15. If you are interfacing a memory with the 8085 which is less than 64 kilobytes, maybe 1 kilobyte, 2 kilobyte, 4 kilobyte, 8 kilobyte, whatever it is, it means not all these memory locations, these address lines, they'll be used for decoding the address. So you use few address lines to identify the memory location. That may be 8 lines, 10 lines, 12 lines, depending upon what is the memory size. And rest of these address lines, so they are combined with some logic circuit or they are used in some decoder circuit to enable this chip. Okay, so then we have write and read signals. If it is a read-write memory, if it is a read-only memory, you have only read signal, no write pin. Okay, and then we have data lines here, input-output lines. Okay, so how now everything is controlled. So what the processor will do, so the processor will send 16-bit address on the address bus, and it comes from your program counter that you know. Okay, so the program counter is loaded with suppose some address. Suppose you are using only 10 lines. If you have 1 kilobyte, it means you are using A0 to A9 only, and then A10 to A15 they are used in the external logic circuit. Okay, if your program counter is loaded with some address, and suppose that address is 2050H. Okay, so which memory location will be identified? Is that so for before that you must know that what is my address range, because you have 64, this processor has capability to address 64 kilobytes, but since we have attached only 1 kilobyte memory, it means you are just using 1024 locations. Okay, so depending upon this hardware connections, so this memory location can take any 1042 bytes from this entire space. Okay, so your, like suppose if it is a 15, 14, then a 13, 12, 11, 10 up to 0. So up to a9, a0 to a9, of course there is but just decoding, so you have 10 bits, so it starts from 0 0. Okay, so rest of the 6 lines, so they can be set to any logic level that you just explained, so that it generates output which is logic 0. So you can set it to any value, that depends upon you. So for that you may have some, this may be connected to some 0 0, suppose 0 0, and it may be suppose 1 1. So this is some hardware that you have decided. Okay, so that when you choose this input combination like this, your output will be 0, which is used to select this or enable this chip. It means now your address will go from 0, this is 0, this is 1248. So 1248, this will become 12, and 12 in your hexadecimal is what? A, B, C, D. So A is your 10, B is 11, C is 12. So it is 0C, 00, and the ending address will be now 0C, F, F. Okay, so this is my address range. It means the processor, now the program can be stored at any location within this address range. Okay, so this will be total 1024 locations now. Okay, so you can store the program at any location, right? It means if you want to identify some address, so you have to load the program counter, which should have the address which should come within this range only. So suppose I load my program counter with some address, suppose 0C, because 0C is now fixed. Okay, of course 0 is fixed, not in fact C is fixed, it will change. So in the next case it can be 1 1 also here, it can be 1 0 also here, and so on. Okay, so if I place some address 0C20 on the program counter, now what the program counter will do, it will place that address on the 16-bit address bus. Now out of this 16-bit address bus, only 10 bits will go to the decoder, that is A0 to A9, and depending upon that those bits, one of the registers in this memory location will be selected. Okay, so rest of the 6 bits, they are fixed and they are used to select this chip, to generate chip enable signal. Okay, so out of these 10 bits only you identify the memory, and then whether you want to read or write the data, you have to just send a control signal from the processor. So if you want to write some information, you send write signal. So whatever is the data on the database, that will go inside that memory location, which is identified by these 10 bits. Okay, similarly if you want to read some information from the memory, so you send a control signal read, the processor will send a control signal read, so that then the memory location which is identified by this address, so the data from that memory location will come on that your database, and it will go inside the processor. The processor then sends it to the instruction decoder, which decodes it, and it comes to know what is the purpose of the instruction, and accordingly it gets executed. executed. Okay, so this is how you interface the memories with your microprocessors. Okay, so in most of the computers, or if see in the laboratory, the single board microcomputers that we use, we do not have 64 kilobytes of memory. Okay, so you may use up to a memory which is up to 4 kilobyte maximum, because the programs that we write, they are very small. Okay, so they can be stored in a small memory chip. So in that case, you have to use this combination. So you can use either a decoder for chip enable, or you can use some external hardware for chip enable. So some bits for this address has to be fixed. They should be connected to the memory chip address decoder. So that depends upon that what is the size of the decoder. Okay.